Hey AP Statistics, welcome to the third part of section 11.1. We're carrying out our Chi-Square goodness of fit test. That's what we're doing. We're seeing if it fits a distribution, a set proportions. We're kind of testing multiple proportions at one time with this. So it is a significance test. It is quite a bit different than all of our other ones we did, though. We get that Chi-Square test statistic and find the p-value. But we got the rest too. We got the check the conditions thing. So good news, this is kind of the same. We still got the random 10% in large counts. It's a little different though. So random, in this case, it is pretty much the same. The data come from a random sample from the population of interest. In this case, in the one example, we're selecting M&Ms. It has to be a random sample of M&Ms, so we know that our sample is not biased. Great news, that's the same. And then the same other condition, when we're sampling without replacement, we need to check the sample size is less than 10% of the population thing. This wouldn't matter for like the die rolling example because you can roll a die forever and ever and ever in theory. We don't have to check that unless we're sampling without replacement. Large counts is a little bit weirder. We need all of our expected counts need to be at least 5. So it used to be like expected number of successes need to be at least 10, expected number of failures at least 10. Now it's just expected counts need to be at least 5 across the board. And that distribution is appropriate. If not, it ends up not matching that chi-square distribution. So we're pretty close to the chi-square distribution as long as we meet that condition. So we already calculated our expected. We just need to go through and verify that our expected counts are at least 5. That kind of threshold we need kind of backs off a little bit from 10. So when checking the large counts condition, make sure to examine the expected counts, not the observed counts, and make sure to write and label the expected counts on your paper or you won't receive credit. You actually have to write out those numbers and then show that they're all at least 5. So then to carry out the test, we pretty much got all the parts we need. So suppose the conditions of the test are met, perform a test of the null hypothesis is that the stated distribution of a categorical variable in the population of interest is correct. Compute that chi-square test statistic, observed minus expected, squared over expected, sum it all up. That's our chi-square test statistic. And then, so that is the sum over k different categories. The p-value is the area to the right of chi-square under the chi-square density curve with k minus 1 degrees of freedom. So let's carry one out. This problem, in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game, specifically because January 1 is the cutoff date for youth leagues in Canada, where many National Hockey League players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time and more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether the player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected and their birthdays were recorded. The one-way table summarizes, not quite a two-way table, we just got we'll get to the two-way tables next section, the data on birthdays for these 80 players. And so we have our birthdays, we got them breaking down into January, February, March, April, May, June, so on and so forth, and we got those observed numbers. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year? We're going to ignore the fact that some months aren't quite as long as others. We're going to call those all a quarter. We're going to expect a quarter in each category. Notice that they're not the same number in our sample. So we got to go through the full state plan do concludes process. Our null hypothesis is that the birthdays of all NHL players are uniformly distributed across the 4 quarters of the year, or the proportions for NHL players in each quarter is the same, all 1/4. The alternative is that the birthdays of all NHL players are not uniformly distributed across the 4 quarters of the year, and we're going to use an alpha level of 5%. So that would be our state. Again, you could also do this writing out the proportions, but I recommend just doing this in words. You could also just say it fits a uniform distribution. We're going with that goodness of fit test. So our plan, we will call this a chi-square test for goodness of fit. Does it fit the anticipated distribution of, 1/4 in each category, uniform? Or we might have some other percentages like the M&M example. Then we need to check our conditions, our random, our 10%, our large counts. The data come from a random sample of NHL players, check. So we need to assume that that is less than 10% of all NHL players. I don't actually know for sure, but yeah, 800. Maybe, not sure. We'll assume it. And if not, maybe it represents NHL players kind of throughout some period of time as well. We'll hope for that. And then the large counts condition, all expected counts are at least 5. We can check that by doing 1/4 of our 80 we would expect here. We'd expect 20. So that's 80 times 1/4 is 20. And then all of our expected would be at least 20. So all expected counts are 20, which is at least 5. Then we go through with the do part of this significance test. So we're going to calculate a chi-square test statistic. We have our observed 32 minus the 20 squared over 20, and then 20 minus 20 squared over 20. Notice that contributes 0, because that's exactly what we would expect. But these other ones contribute. So being high, we can contribute to the chi-square test statistic, and being low, we can contribute to the chi-square test statistic. So calculating that out, we get a chi-square test statistic of 11.2. The degrees of freedom is 4 categories minus 1, so 3. And so if we use the table, which, chi-square CDF, lower from 11.2 up to infinity with 3 degrees of freedom gives us that p-value of 1.1%. So because that p-value of 0.011 is less than alpha 0.05, we reject the null hypothesis. We have convincing evidence that the birthdays of NHL players are not uniformly distributed across the 4 quarters of the year. So seems like, yeah, we don't actually immediately conclude what the result is. All we say is it's not uniform. That's all this chi-square really says. For us to do it, we got to follow that up with a little more analysis. So if you're going to do this in your calculator, what you can do is you can do a chi-square goodness of fit test, and really they make you do a lot of work for this. This calculator program is kind of weak. But you have to put your observed, and you can put them into like list 1, and then your expected into list 2, and then when you go to calculate that, you're going to look up, you're going to go to stat test, and you're going to go scroll all the way down to chi-square goodness of fit test, GOF test, and you have your observed in L1, your expected in L2. You tell it the degrees of freedom, which is in this case is categories minus 1, which again the programming should have been able to do that for you, but they didn't put a lot of effort into this one. And then you can have it calculate that chi-square test statistic for you and the corresponding p-value. So you can, there's the calculator version of this as well. And then this is kind of neat. This is the contribute list. That is what they contribute to the chi-square value. So which one's the furthest off, right? So in this case, it's the January month. That's the furthest off. It's way more than we would have expected. So that's 7.2. If we kind of go way back here, is what we got in this part right there. So the 7.2, the 0, the 0.8, and the 3.2. That's what our calculator tells us when we run that chi-square goodness of fit test. So that's nice. Note when you run the chi-square test for goodness of fit on the TI-84 calculator, the list of individual components will be produced and stored in the list called contribution. But that is, that list is in your, if you go second list, is in your calculator now. AP exam tip, you can use your calculator to carry out the mechanics of a significance test on the AP statistics exam, but there's risk involved. If you just give the calculator answer with no work and one or more of your values is incorrect, you will likely get no credit for the do step. So we recommend writing out the first few terms of the chi-square calculation followed by the ... the ellipsis. This approach might help you earn partial credit if you enter a number incorrectly. Be sure to name the procedure chi-square test for goodness of fit and report the chi-square to the test statistic, chi-square, and the degrees of freedom and the p-value. So you can report that stuff. You can do it completely in the calculator, but they kind of say, do a little bit by the formula. So like, you do your first observed minus expected squared over expected, your second one, and then, maybe fill all that one up with a ... so you don't have to write out the whole thing because it can get quite long. So then finally, follow-up analysis. If the sample data lead to statistically significant results, we can conclude that our variable has a distribution different from the one stated, but the chi-square doesn't actually tell us how it's different. So to investigate how the distribution is different, start by identifying the categories that contribute the most to the chi-square statistic. So in our birthday example, if we looked at the observed, the expected, and then did the whole observed minus expected squared over expected, the seasons or the quarters that contribute the most are the first and the last one, and January to March is the most. And so once you identify those, then we can kind of analyze it a little further and really just kind of describe what's going on. In October through December, 8 fewer players were born than expected. In January through March, 12 more players were born than expected. And so you can say that, there seems to be evidence that, that could be the reason that those months, in the middle, it doesn't seem to have as much of effect, but the real old relative players and the younger players relative to their year were either over or underrepresented. So you can do a little more analysis with that once you get it. And you could, even break it down and just focus on that and do one proportions intervals and things like that. So that is the chi-square goodness of fit test.